Hello, everyone, and welcome to my presentation. My name is Will Thorpe. I'm a section engineer working for Morgan Sindall Construction and Infrastructure in London, in the UK. So my presentation will be on the Thames Tideway project in London, and specifically the Hammersmith connection tunnel. Before I get started, I'd just like to thank Sandeep and the committee for inviting me to speak at this symposium. It's a great opportunity to be able to share my knowledge with other engineers. So, and also I'd just like to apologise for not being able to speak live at the event, but hopefully this recording will be just as good. Just a little bit about myself, briefly. So I studied an MEng civil engineering degree at Warwick University, as well as an MSc in tunnelling and underground space. I went on to then work for Morgan Sindall Engineering Solutions. This is a design consultancy business specialising in the design of tunnels and underground structures. After a short period working for them, I went on to work for the Major Projects division, where I worked as a site engineer on a few different tunnelling projects around the UK. And then in 2018, I began work at Hammersmith on this current project, where I worked as an SCL engineer and also a section engineer for the shaft internal structures works here as well. So I've been working here since then for around the last 3.5 years. Okay, so just a little bit about the Thames Tideway Tunnel project. I'm aware many of you might not know anything at all about this project in London, but it's one of the biggest tunnelling infrastructure projects in the UK at the moment. So the tunnel is a 25-kilometre long sewer tunnel bored predominantly underneath the River Thames, as you can see here. The main purpose of the tunnel is to capture current sewer overflows that dump approximately 36 million tonnes of raw sewage into the River Thames every year. So the tunnel is split up into 3 main contracts of work, shown here at the bottom. So there's the west, central and east sections, totaling the 25-kilometre length. I've been working on the west section, which stretches from the Carnworth Road site at number 7 to Acton in the west of London. At number 2 is the Hammersmith pumping station site, which consists of a 300-metre long connection tunnel, which I'll come on to. So outlined here is the site itself, highlighted in the white box. So the site has a number of constraints. First of all, it's an incredibly small site compared to the amount of work which is going on there. So there has been a lot of planning and difficulties involved around scheduling the works and planning it and programming it correctly in order to minimise any disruption to other parts of the site. And then, as you can see, the site is situated in quite a residential area in London, close to the River Thames. As well as residential houses, there are also high-rise flats directly adjacent to the site. So this has given us a number of constraints in terms of the amount of noise and vibration and the working hours during the project. So quite a difficult site to work at in terms of those constraints, but it's been a good challenge. Okay, so shown here in this graphic is the most of the underground structures that we have built at Hammersmith. As I mentioned earlier, the main purpose of the project is to capture any overflows, sewer overflows that occur and spill into the River Thames. This happens pretty much whenever it rains in London. So the whole project is basically upgrading London's sewer system to cope for at least the next 120 years of population growth. So shown here in yellow is the existing pumping station. This was built in the 1960s, and this will remain in place. And then also an existing structure is the inlet channel. So to the far left of this image, you can see the two sewer inlets into this channel. This is where all the existing flows enter the pumping station from the huge Hammersmith catchment area. And then to the left of this is the interception chamber, and this is where the new structures begin. So we've built the chamber. Connecting the chamber and the shaft is a culvert. So this directs the flows across the site towards the shaft. And then the flows transfer down inside the shaft in a stainless steel vortex tube, which you can see in the center of the shaft there, and then into the connection tunnel. So the connection tunnel is 300 meters long, and this carries the flows towards the main Thames Tideway tunnel. So a few little details there about the shaft and the tunnel. Both were constructed with sprayed concrete for the primary lining. So this is predominantly what I'll focus on. The primary lining diameter, internal diameter of the shaft was 11.5 meters with a thickness of 425 millimeters. The total depth of the shaft below ground level was approximately 33.5 meters. The connection tunnel, so that has a primary lining internal diameter of 4.5 meters and a thickness of 325 millimeters. And as mentioned, the length is just under 300 meters long. So this just gives you a bit of a better perspective of the site. That shows the full length of the tunnel and where it connects into the main Thames Tideway tunnel in the bottom left corner. At the time of construction of the tunnel, the main Thames Tideway tunnel hadn't yet been constructed, so there was a TBM chamber constructed at the end of the tunnel, where later the main drive for the tunnel would intercept this and connect the Hammersmith tunnel to the main Thames Tideway tunnel. Okay, so just a little bit about the shaft and its excavation and construction. The shaft was constructed predominantly through London clay, shown here on the left. London clay is a good medium to tunnel through, and this was done with a series of 30 advances, which were 1.2 meters in depth. Towards the top, through the first few excavation advances that were carried out, these were through made ground and river terrace deposits. So there were secant piles installed prior to the excavation of the shaft for approximately the first 10 meters of the excavation. So this continued down. Shown on the right-hand side, you can see that the primary lining was sprayed in two main layers. This was predominantly in order to stagger joints and basically create a more onerous water path to help any groundwater, to prevent any groundwater from seeping into the shaft. So the connection tunnel design, it was based on a composite structure design which allowed load transfer between the primary and the secondary linings. So the primary lining was a steel fiber reinforced sprayed lining, and this was constructed in 1 meter advances. The secondary lining was a cast in situ lining, grade C4050, and there was no waterproofing membrane specified between the two linings. Instead of this, a crystallization agent was used, which was added into the primary lining mix. This is called Zypex. And Zypex, it's as I said, is a crystallization agent. It was an admixture used, and it increases the impermeability of the mix. So it mixes with cement and active chemicals, and when it reacts, it with the moisture and the byproducts of cement hydration, and it creates a catalytic reaction. This helps generate a non-soluble crystalline formation throughout the pores of the concrete, and it helps prevent water penetration through the linings. So as you can see in the picture on the left, it's done its job for this shaft, and it's helped create a nice dry primary lining. So for the connection tunnel, this just shows a series of different sections during construction. So section 1, this was referred to as the deaeration chamber, shown in red. So this is for the first 50 meters of the tunnel. When flows enter the tunnel, they have just dropped down the vortex tube, and they'll have a lot of entrained air within the sewage. So the first 50 meters of the tunnel is actually a slightly larger diameter, 5.6 meters primary lining ID, and this was to help settle down the flows before entering the rest of the tunnel. Also within this section of the tunnel, there's a deaeration shaft, a slightly smaller shaft, which is designed to help ventilate the sewage and to remove this trapped air. Moving on then to section 2, advances 52 through to 116 of the tunnel. So these were this was 4.5 meter internal diameter. And then in section 3, there was a passing point designed into within the design of the tunnel. This was purely to allow plant to pass one another within the tunnel during construction. So this was just for a construction purpose only, and then this was sprayed to the 4.5 meter diameter following the finished construction of the tunnel. Section 4 then continued underneath the River Thames at 4.5 meters diameter, and then section 5 advances 287 to 295, where we constructed the TBM reception chamber, which involved increasing the diameter slightly. So this graph shows the actual production achieved during the construction of the tunnel. The primary lining of the tunnel was fully constructed within just under 6 months. It began in August of 2018 and was completed in January of 2019. On average, we achieved an advance rate of around 20 meters per week. And as you can see, we managed to meet the program quite well and stuck to our target advance rate. Okay, so just a little bit about the excavation and geology. The tunnel was entirely excavated through London clay. There were 2 different units called Unit B and Unit A3II. These don't hugely differ from one another. However, because of this, we encountered some faulting in the face. So you can see throughout the center of the face shown here, there's a horizontal band of claystones, which were commonly encountered throughout the tunnel drive. And you can see a small fault line present in the center due to the vertical displacement of the 2 lines. There was some minor instability of the face at times due to some wedge failure, which you can see in this face log here, just at the top. And the tunnel was dry throughout, no major water ingress at all. So a couple of photos here during construction, shown here on the left. This was the plant used to excavate the tunnel. This is a Schaef ITC120 excavator. So this has an arm with a toothed bucket at the front. It has an apron in order to collect the excavated muck, and then a conveyor belt which runs through the machine and will load up the tracked dumpers which we used through the tunnel. These would then take the muck back to the pit bottom to be removed from site. So as you can see, quite tight working areas, not a lot of spare room. So quite good exclusion zones, and good practice was implemented here to prevent any incidents. On the right is the finished primary lining. So we had just completed mucking out the tunnel, mucking out the invert to prepare the tunnel for the secondary lining prior, just following this photo. Secondary lining of the tunnel was constructed using a shutter, a bespoke shutter produced by Kern. The shutter was 6 meters long, and we were originally aiming for an average of 3 pours per week during the construction of the secondary lining. However, once the gang built up some momentum, we actually managed to achieve a pour every day, working 5 days a week. So we actually got 5 pours a week at the peak production rate. During the secondary lining construction, there were 2 gangs working a day shift and a back shift through Monday through to Friday. So the general sequence of works would be that the day shift would come in to a shutter which was ready to be poured in the tunnel. We'd pour that on the day shift immediately, and then we would strike the shutter a few hours later and be able to actually move the shutter within the tunnel that same day. And the back shift would then come in and prepare and set the shutter and install the timber stop ends required to pour the next morning. So there's the completed shutter, ready to be lowered down within the shaft. The shutter was then moved to the far end of the 300 meters of the tunnel, where the first pour was undertaken. So the concrete was delivered to site by normal concrete wagons and pumped the full 300 meters down the tunnel. This was achieved quite well. And then this continued for around 49 pours in total in order to complete the secondary lining. So a couple of pictures here from the completed tunnel now. Overall, a really good finish achieved on the secondary lining, as you can see. And on the right-hand side, you can see at the far end of the tunnel there, that is the TBM chamber, which was constructed and then backfilled with a foam concrete in order for the TBM for the main tunnel to break through. Finally, I just want to pick up on a couple of health and safety topics, a couple of interesting ones which we implemented at Hammersmith. So we realized that concrete lines were subject to wear on the bends, particularly down when the concrete comes down the pipelines in the shaft, and when it hits the outside of any bends in particular. So we implemented weekly checks on the thickness of the pipes. We used an ultrasonic pipe thickness tester, and then we would enter the shaft with the man rider basket on the crane, and we would spend an hour each week checking these pipes for wear. Any warm pipes could potentially pose a risk of concrete splashing onto operatives in the pit bottom. So there were a number of cases where we found that bends on the pipe were excessively worn, and then we would obviously then replace these sections of pipe as required. Finally, one of the most dangerous things about tunneling and SCL tunneling is when you come to blow out the lines. So quite commonly, compressed air is used, which has resulted in many incidents throughout the tunneling industry to date. However, at Hammersmith, we did it differently. So we wanted to use water instead of compressed air to wash out the lines, which is much safer. So this is a little schematic showing the setup. So it's quite simple, concrete line and the water line in the tunnel. We had a mono pump set up in the pit bottom and also a washout skip. So following the completion of a sprayed advance, the concrete line would be split at the point of spraying, and then blowout balls inserted into the end of the line at the tunnel face. This would then separate the water from the concrete, and then a washout cannon would be clamped onto the end of the concrete line, and then the water line would be connected up to the washout cannon. Operatives would then radio back to the pit bottom to confirm it was all connected up, and the monopump would then be turned on in order to flush out the concrete into the washout skip back in pit bottom. Once that had been completed, then the pump would be reversed once they had confirmed that they'd received those washout balls in the pit bottom. So this is a really good scheme that we did at Hammersmith here in order to improve the health and safety, and would definitely recommend it to anyone who might be planning something similar in the future. So that's about what I've got. Thank you very much for listening. As I said, I'm sorry it's not live. However, hopefully you've enjoyed it.